Welcome back to Little Bang Discovery Plus. Last time we talked about air and how it's always there even though we don't usually notice it. So if you haven't had a chance to talk to your grown-up about what we did last week, what you might have done since, and any new ideas you have, now's the time to have a little chat about what you think you know about air now. Now this session is all about chemical change and visually representing results. Chemical change is different to physical change that we did a couple of sessions ago. You might remember that physical change was solids, liquids and gases, and the teddies demonstrated that for us, and we did some experiments with those. Chemical change is when things change, when you mix things together. Can you remember what happened in our first session when we added the salt to the water? What happened to the water when we added salt to it? There was a chemical change happening there. So what do you think you know about chemical change? Here are a couple of questions to help you. As well as what happened to the salt, what about the other things that we did in another session where we dissolved things in water or tried to? What happened to those substances when they were added to water? And another thing to think about is, have you ever seen how much space a cake takes up before it goes into the oven, and then how much space it takes up when it comes out of the oven? So there's a change in how much space it takes up, the volume of the cake, and a chemical change has happened there to make that change. So let's do our first experiment for today. We're going to start off with a couple of cups or glasses with some water in them. So here we are with our measuring cup once again, and we're going to try and get 150 mils, which is the amount that we've been using all this time. So measure it quite accurately. You might want to use your syringe or your pipette or your eyedropper if you put a little bit too much in, like I have, to take some out. Or if you need to add just a little bit more, you might want to add a little bit more with them. So there's 150 mils for this one. And I need a second cup with 150 mils in it. Okay, that one's pretty close. So I'll put that in. Now, what we're going to do is we're going to add a tablet to these cups. You might have a Berocca tablet, or you might have a Hydralyte tablet. Either of those will work for this experiment. And what we're going to do is we're going to add one of the tablets, so here it is, and then we're going to time how long it takes before it dissolves. So get your timer ready. It might be a clock with a second hand, it might be on a phone, or it might be a little timer like I've got. And I'm going to put it into one of the cups and start my timer. And there's a change happening. I can see some fizzing going on. And I don't know if you can see the tablet in there. It's fizzing and bubbling away. There's lots and lots of bubbles in my glass, and I can hear the bubbles popping at the top, and it's quite hard to see. Oh, there it is. It's still going, still fizzing away. Now it's floated up to the top. I can still see it in the top. There's still a little bit there, still bubbling away. So far it's been 48 seconds. It's very small now. It's smaller than a 5-cent piece now. So it's nearly finished. And it's about to all dissolve, and I stopped my, yep, it's all dissolved. I've stopped my timer. That took 1 minute 15 0.57 seconds. So I'm going to write that down in my discovery diary because I don't think I'll remember that unless I do. So my whole tablet took 1 minute, 15 seconds and 57 1/100ths of a second. Now my second tablet I'm going to crush up into small pieces. So I'm going to do that inside this piece of paper towel. You might need to get your grown-up to help you with this. So actually my paper towel's breaking. So I'm going to try and make it as small as I can, small little bits, and then I'm going to put it in here. So my tablet now is much smaller than it was, lots of little pieces. Do you think that will make a difference to how long it takes to dissolve? So it's going into 150 mils of water, the same amount, but the pieces are much smaller now. Do you think that will make a difference? Have a guess, make a prediction, talk to your grown-up about what you think will happen. So I need to put my timer back on 0. Okay, it's ready. Now I'm going to tip all of these in at once into my water. I'm expecting it will fizz again, but will it take 1 minute 15 seconds or will it be a different time? Here we go. Ready, set, go. Okay, so it's fizzing away. Fizzing away. I can't see any big bits, seeing as how I've made them quite small. They're all on the top, fizzing away, and stop. It's finished now, and that only took 24 seconds and 72 1/100ths, so no minutes, 24 seconds. So it took much less time when the tablet was broken up than when it was whole. Why do you think that might be? You try the experiment if you haven't done so yet. See what results you get and talk to your grown-up. And in the meantime, I'm going to put some dots on my graph to show how long it took when it was a whole tablet and how long it took when it was a short tablet, when it was a broken up tablet. So you might like to make a drawing in your discovery diary to show that. So here's my graph. 15, 30, 45, 60, 1 minute 15 seconds. When it was a whole tablet, it took 1 minute 15. When it was crushed tablet, it only took 24 seconds, so much less time. So the pattern here is that the whole tablet takes much longer, whereas the crushed tablet takes much less. So we had a lot of fizzing happening in the water, so there was a chemical change going on. Now we're going to do another experiment where there's a chemical change. So to start off with, you need some vinegar. So I've got my vinegar in a squirty bottle, but you might have it just in a normal bottle from the supermarket. And you need to squirt about 2 centimetres depth, or pour about 2 centimetres of vinegar into the bottom of your cup. So I'm just going to see how I'm going, if that's close. Oh, that's pretty close to 2 centimetres. And now I want to do the same thing in the second one. So I'm going to use it to compare. Maybe not. Okay, we'll see what happens. Now, to the first cup, I'm going to add about a teaspoon, and it doesn't have to be level this time, it can be heaped up, of bicarb soda, bicarbonate of soda. and see what happens. Now, before I do that, talk to your grown-up. Do you think anything's going to happen? Will this just dissolve like the salt did in the water and make it go cloudy? Or will something else happen? What do you think might happen? Have a guess. And let's try it. Okay, so once again, I've got bubbles happening. A lot of bubbles at the top there. So there's a chemical reaction, and I can see bubbles down in the vinegar. So there's a chemical reaction happening. Now, when we did our experiment with air last session, the bubbles meant that the air was coming out, so there was a gas coming out. So that means that there's a gas coming out of this chemical change as well. Okay, now let's try that again, and this time let's really look at the bubbles and see if they remind you of anything. So we put in our spoon of bicarb, and we've got lots and lots of bubbles. It's almost a froth on the top there, and there are bubbles in the vinegar. And do they look like something you might have seen before? Talk to your grown-up about whether these bubbles look familiar to you. Have you seen bubbles like this before somewhere? Now the place that you might have seen the bubbles is in soft drinks, because the bubbles in soft drinks are made of carbon dioxide. And that was what these bubbles are. They're bubbles of carbon dioxide. So the one that I set off first now actually looks a bit like lemonade with the bubbles in it. So the chemical change that happened, we ended up with a gas being made, and that gas was carbon dioxide, which is the gas they put into soft drinks to make the bubbles. Now this time we're going to do an experiment and try and trap the carbon dioxide. What could we trap the carbon dioxide in? Remember, it's a gas. It likes to come out and go wherever it can go and fill up the whole space. So what could we trap our carbon dioxide gas in? See if you can have a think about that with your grown-up. What can I use to trap the gas? So I need to sort of have something up here to trap the gas that's coming up. The thing that I'm going to use to trap the gas is a balloon. So what I'm going to do is put my vinegar into this bottle. So about a depth of about 3 centimetres this time. So about there. Now I have to be careful when I put the bicarb in so that I can catch it in a balloon. So what I'm actually going to do is use a funnel to put the bicarb into the balloon. So I'll put in a couple of spoons of bicarb. Now it tends to clump together and not go in nicely, so I'm actually going to use a skewer to poke it down. So now I've got a balloon with bicarb inside it. Now if I very carefully put this on the bottle without lifting it up, I've still got the bicarb in the balloon, I've got the vinegar in the bottle, and I want to make sure that the balloon is on really well so that no gas can escape out the sides. So check that my balloon is down nicely. Now, what do you think will happen when I lift up the balloon and the bicarb can fall into the vinegar? Make a prediction, talk to your grown-up. What do you think will happen to the vinegar, to the bicarb, and to the balloon, and maybe the bottle? What might happen to all those things? All right, let's try it. So I'm going to lift up the balloon, shake in the bicarb, And what's happening to my balloon? Can you see how it's inflated? So it's trapped the carbon dioxide and it's now full of carbon dioxide. Now, if you wanted to try this experiment with a bigger bottle, with more vinegar and more bicarb soda, how much carbon dioxide do you think you get? Do you think you would get more than what I've got? So I'm going to very carefully take this off and try not to let the carbon dioxide escape. Stuck it down so well that I'm having trouble. Actually, what I'll do first, I've got a balloon closure. I'll put that on. So you might not have one of these. So you'll just need to, hopefully your balloon is not proving as difficult to get off. There we go, I'm getting it off now. So there's my balloon full of carbon dioxide. Now, when you normally play with a balloon, is this what it's like? Does it fall down that fast? You might actually like to get another balloon and blow it up to the same size, so not very much. I haven't got a lot of carbon dioxide there. So blow it up to about the same size. Close it off. So this blue one is full of air. This black one is full of carbon dioxide. If I drop them, do you think they'll do the same thing? Have a guess. Make a prediction with your grown-up. What do you think will happen? Okay, let's try it. So I'll just move some of these things out of the way so we can see a bit better. Okay, the black one's got the carbon dioxide in, the blue one's got the air that I blew into it. Let's see what happens when we drop them. Oh, they look pretty similar, but if you play with them, do they feel the same? Carbon dioxide is actually quite a heavy gas and usually sinks, which is why it's used in fire extinguishers, because it sinks and smothers the air away from the fire to help put the fire out. So this one might feel different to this one. All right, so these are our chemical changes that we've seen. We've seen the Hydralyte or the Berocca tablets fizz and make bubbles, make a gas, so there's a chemical change happening there. We saw the vinegar and the bicarb also fizz and make a gas. We managed to catch some of that carbon dioxide gas in our balloon when we put it on our bottle. So chemical changes is when you put in two things and they mix together and make new substances. That's what a chemical change is. So I'd like you to think about what we've seen today. Is there new stuff here that you've learned? Have your ideas about chemical changes changed? So talk to your grown-up about that. Perhaps you might like to, if you haven't drawn your graph yet about your, this way, about your tablets, you might like to draw a graph, because today we're concentrating on visually representing results, so that means drawing graphs. You might also like to draw a picture of what it looks like when the vinegar and the bicarb mix with all the bubbles and frothing happening. So that's another way you can visually represent your results. And then we've got some extra activities for you. For example, you might use another Hydralyte tablet, and instead of having a whole tablet, just put in a half tablet. Does that mean the time will be half the time? So you could make a prediction about that and test it. You could try putting it into warm water. Does that make a difference? You could try putting it into iced water. You could try putting 2 tablets in at once. Will that make a difference to how long it takes to dissolve? So there are some variations on the Hydralyte experiment that you can do. Another thing that you can do is you can make invisible ink. And the way to make invisible ink is to get some lemon juice. So juice your lemon, put it into a little dish, add a little bit of water to it, just a drop, not a lot. So bit of lemon juice, bit of water, stir it up with a cotton bud, and then you can use the cotton bud to write a message in your discovery diary. So write a message and leave it to dry, and it will go nearly invisible. You won't be able to see what you've written. But the way to reveal the message is to apply some heat to it, and an easy way to do that is to get the hairdryer and blow the warm air onto it. And then a chemical change will happen to the lemon juice, and it will turn brown, and you'll be able to see your message. So that's the way to make invisible ink with lemon juice. And the other thing that you might try, on your list of equipment that you've received about all the stuff that you need, for this session there is a recipe for a chocolate cake. And you can make one layer of the chocolate cake using baking powder, which is similar to bicarb. And you can use one layer of the chocolate cake without baking powder and see what difference it makes to the cake after it's been cooked. So there's the recipe on your equipment list. One of them you add the baking powder, one of them you don't. Bake it in the oven and see if there's a difference to how much the cake rises. And also included on that equipment list is a recipe for chocolate icing to put on both of the cakes. So you can put the cakes together to make a double layer cake if you want to, or you can keep them separate. So a chemical change is happening when the cake is in the oven to make it rise. And you'll see what difference it makes if you leave the baking powder out. Okay, so that's chemical change and visually representing results. So it'd be good to do some drawings or make some graphs, as well as trying a couple of extra experiments about chemical change.